For decades, electronics have been designed around one unspoken rule. They must remain rigid from the earliest circuit boards to modern silicon chips. Electronic systems were forced into flat, immovable forms even as the world around them remained dynamic, curved, and alive. This limitation shaped everything from consumer devices to industrial machines. And even today, many advanced systems still depend on stiff boards and fragile interconnections. But technology does not evolve by accepting limits, it evolves by breaking them. In this video, we go beyond the blueprint to explore how advanced 3D printing is redefining the fabrication of flexible electronics, enabling circuits that move, bend, stretch, and integrate seamlessly into the physical world. Flexible electronics are not simply a new category of components. They represent a philosophical shift in engineering design. Instead of forcing the environment to adapt to electronics, electronics now adapt to the environment. These systems are engineered to follow the natural motion of surfaces, whether it is human skin, textile fibers, robotic joints, or organic structures, by using flexible and stretchable substrates. Circuits can maintain electrical performance even under continuous mechanical stress. This shift changes how engineers think about reliability, durability, and interaction, especially in applications where electronics must coexist with motion rather than resist it. Traditional electronic manufacturing methods were optimized for precision on flat, rigid surfaces, not for adaptability. Processes like photolithography and chemical etching require controlled environments, expensive equipment, and multi-step workflows that leave little room for customization. These methods work well when producing millions of identical chips, but they struggle when flexibility, rapid iteration, or complex three-dimensional geometry is required. As technology moves toward personalization, reliability, and integration with soft systems, these rigid manufacturing approaches reveal their limitations, creating a gap that advanced 3D printing is uniquely positioned to fill. Advanced 3D printing does not simply replace existing manufacturing methods, it introduces a new way of thinking about fabrication itself. Instead of separating structure, function, and electronics into different production stages, 3D printing merges them into a single continuous process. Conductive materials, insulating layers, and mechanical structures are deposited exactly where they are needed, forming fully integrated systems directly from digital designs. This approach dramatically reduces development time and allows engineers to test, modify, and optimize flexible electronic systems faster than ever before. One of the most powerful changes introduced by advanced 3D printing is the transition from two-dimensional circuit design to true three-dimensional electronic architecture. Traditional circuit boards force components and connections onto flat planes, while 3D printing allows circuits to follow curves, wrap around structures, and extend through volumes. This capability is especially critical for flexible electronics, where mechanical and electrical performance must be balanced simultaneously. By designing circuits that align with stress patterns and deformation paths, engineers can dramatically improve durability and functionality. Direct ink writing plays a central role in the fabrication of flexible electronics, as it enables the precise deposition of conductive and functional inks onto soft substrates. These inks are carefully engineered to flow during printing while maintaining conductivity after curing. As the printed material stretches or bends, the conductive network inside the ink deforms without breaking, preserving electrical pathways. This technique allows engineers to create sensors, interconnects, and signal paths that remain operational under repeated mechanical stress, making it ideal for wearables and soft robotic systems. Inkjet and aerosol jet printing techniques push precision to the microscopic scale, allowing conductive traces to be printed with extreme accuracy on flexible surfaces. These methods enable electronics to be deposited on thin films, curved objects, and even fully assembled components. Aerosol jet printing, in particular, allows circuits to be printed in three dimensions without contract, making it possible to fabricate electronics on complex geometries that would be impossible using traditional techniques. This capability opens the door to true conformal electronics that seamlessly integrate with their host structures. While high-end printing techniques dominate research labs, modified FDM printers bring flexible electronics closer to makers, students, and independent developers by using conductive filament and flexible thermoplastics. These systems allow structural components and basic electronic pathways to be printed together. Although conductivity remains lower than industrial methods, this approach democratizes experimentation and education, enabling rapid learning and innovation at a low cost. It also plays a crucial role in prototyping and early stage development before transitioning to advanced manufacturing systems. Material science is the foundation that makes flexible electronics possible. Conductive materials must maintain electrical performance while tolerating bending and stretching. And substrates must support both mechanical durability and electrical insulation. Advanced nanomaterials such as graphene and carbon nanotubes create conductive networks that adapt to deformation, while elastomeric polymers provide the mechanical flexibility needed for real world applications. The interaction between materials geometry and printing parameters determines whether a flexible electronic system will succeed or fail under continuous use. One of the most transformative capabilities of advanced 3D printing is the embedding of electronics directly inside printed structures. This approach eliminates external wiring, reduces assembly complexity, and protects sensitive components from environmental damage. By pausing the print process to place components or print conductive paths, engineers create intelligent objects that are self contained and structurally optimized. This technique is particularly powerful in robotics, where embedded sensing and control systems improve performance without adding bulk or weight. Flexible electronics play a vital role in the evolution of soft robotics, where traditional rigid sensors fail to capture complex deformations. By embedding flexible sensors directly into soft actuators and structures, robots gain the ability to sense touch, pressure, and movement in a way that mimics biological systems. This integration allows soft robots to interact safely with humans and adapt to unpredictable environments, pushing robotics beyond rigid machines toward truly intelligent, responsive systems. A medical applications, flexible electronics fabricated through advanced 3D printing enable a new generation of patient-centric devices. Skin-mounted sensors conform naturally to the body, reducing discomfort and improving signal quality during long-term monitoring. Implantable systems benefit from soft, biocompatible materials that reduce immune response and mechanical irritation. These technologies support continuous health monitoring, early disease detection, and personalized treatment, making a significant shift toward proactive healthcare. Renewable technology is undergoing a fundamental transformation as flexible electronics move from rigid models to seamless integration within textiles. Advanced 3D printing allows sensors and conductive pathways to be printed directly onto fabrics or embedded within layers of clothing. This approach eliminates bulky enclosures and creates garments that feel natural while providing real time data. As a result, wearable devices become less visible and more intuitive, blending technology with daily life rather than interpreting it. Industries such as aerospace and automotive engineering benefit significantly from flexible electronics and 3D printing integration by embedding sensors directly into structural components. Engineers can monitor stress, temperature, and fatigue in real time without adding extra weight. This capability enhances safety, reduces maintenance costs, and extends the lifespan of critical systems. The ability to fabricate electronics directly onto curved and load bearing surfaces represents a major advancement in industrial design. Despite rapid progress, advanced 3D printed flexible electronics still face significant challenges. Electrical performance often lags behind traditional copper based systems, and long term durability under extreme deformation remains an area of active research. Manufacturing speed, scalability, and material cost also limit widespread adoption. However, these challenges are not barriers but catalysts driving innovation in materials, printer design, and hybrid fabrication techniques. The future of flexible electronics lies in deeper integration, smarter materials, and autonomous design processes. AI driven optimization will generate electronic architectures that balance electrical performance and mechanical resilience. Emerging techniques like 4D printing will introduce time based functionality, allowing electronics to change shape or behavior after fabrication. As this technology matures, electronics will no longer be manufactured as separate entities but will emerge as inherent properties of objects themselves. We are entering a new era where electronics are no longer trapped inside rigid boards and fixed shapes, but instead become flexible, adaptive, and deeply integrated into the physical world around us. Advanced 3D printing is not just improving how electronics are made, it is redefining what electronics can be, allowing circuits to bend, stretch, and live inside structures, robots, wearables, and even the human body. If this video helped you understand the future of flexible electronics and advanced fabrication, don't forget to like the video. It really supports the channel. Leave a comment below with your thoughts or questions and subscribe to the Career Robotic channel for more deep content on robotics, electronics, and advanced technologies. New videos are coming very soon, so stay connected, keep innovating, keep building, and as always, go beyond the blueprint.